Suppose you have random number 56 molecules of a strong acid in aqueous solution. If 100% of these molecules dissociate, how many H+ ions will be present in the solution? This should be a trivial question, very easy to answer. 100% of 56 is 56. And that will be the number of H+ ions present in the solution. In reality, these will be H3O+ ions, but we can call them H+ ions for simplicity's sake. Alright, this next sentence says the percent dissociation described in the problem is redundant, meaning we didn't need to say that, because a strong acid always dissociates completely, meaning 100% dissociation. So any molecule that has this sort of behavior, where it dissociates, does not reassociate, must have 100% dissociation. HX simply turns into H+, and X-, 100%. Next question. Now we're dealing with a specific weak acid, and we're dealing with molarity. Suppose you have a solution labeled 0.02 molar HCl. What is the molarity of H+ ions in this solution? So now the concept is the same, but the numbers are a little bit scarier. 0.02 molar is actually a very large number of molecules per liter, because Avogadro's number is so huge. So all we need to do here is say it's still 100% dissociation. What's 100% of 0.02 molar? Well, it is simply 0.02 molar H+ ions. Again, these would be H3O+ ions in real life. The last question in this section says use a calculator to find the pH of the solution. We can actually do this without a calculator if you remember the concept of I can do logarithms. So the H+ ion concentration, which is represented by H+ in brackets, is 0.02 molar, which is 2 times 10 to the minus 2 molar. pH is the negative logarithm of the H+ ion concentration. So if we take the log of 2 times 10 to the minus 2, that'll be a negative value, but we'll make it a positive by using this negative sign here. If we take the log of 2 times 10 to the minus 2, that would be 0.3 for the log of 2 and -2 for the log of 10 to the minus 2. So the log of 2 times 10 to the minus 2 is equal to -1.7. But for the pH, we invert the sign. Therefore, the pH is 1.7. Final answer. Part 2 is now talking about a weak acid. And a weak acid will not have 100% dissociation. So now we actually have to do some calculations. Suppose you have random number 120 molecules of a weak acid in aqueous solution. If 5%, that's a reasonable percent dissociation for weak acid. If 5% of these weak acid molecules are dissociated at equilibrium, how many H+ ions will be present when the solution reaches equilibrium? So we're taking 5% of 120. That mathematically would be 0.05 times 120, or you could simply think of it as a 20th. 1/20th of the molecules, that's what 5% represents, will be dissociated. So 1/20th of 120 is 6 H plus ions, 6 X minus ions, which would mean 114 HX molecules. So this is what's present at equilibrium here. All right, when we get to B, now we're talking about molarity instead of individual molecules, but the concept is the same. Let's say we have a 0.25 molar solution of a weak acid. In aqueous solution, a small percentage will be dissociated. Let's let it be 1%. If 1% of the weak acid molecules are dissociated at equilibrium, what will the molarity of H plus ions be? Alright, so we're taking 1% of 0.25 molar. That would be 0.01 is 1% times 0.25 molar. So if you understand percents, I'm just moving the decimal over 2 times. So I get 0.0025 molar H plus, which I could write as 2.5 times 10 to the minus 3 molar H plus. Again, most of this 0.25 molar, 99% of the 0.25 molar HX is still in the associated form. Now we're going to find the pH of this solution. The H plus ions determine the pH. This right here does not affect the pH. That's the HX molarity, but the H plus molarity is what counts. So start with what is the truth. pH is the minus log of the H plus ion concentration. pH equals minus log of 2.5 times 10 to the minus 3 molar H plus. Again, you can use a calculator, but you can also go without if you know the log of 2.5, which happens to be 0.4. Log of 10 to the minus 3 is negative 3. So the log here is negative 2.6. The pH therefore equals 2.6. Two more problems here. Suppose you have lactic acid, a weak acid, and let's make up a number here. Let's say it's 0.34 molar solution of aqueous lactic acid. A small percentage of the acid will be dissociated. Let's imagine that the molarity of H plus ions is 0.020 molar. What percent of the lactic acid molecules are dissociated at equilibrium? This is a simple calculation where we just take the fraction that is dissociated, 0.02 molar, divide by the total molarity that was originally present, and we get the percent dissociation. This one I will need to use a calculator because it's not a real nice number. So I'm dividing my 0.02 by the 0.34, and I get 0.0588, which is 5.9% dissociation. That does indicate that 94.1% of the lactic acid molecules are in their associated state. Last question says determine the pH. You should know how to do that. Explain your method. If you're using an equation, you write the equation. pH equals minus log H plus ion concentration. In this case, the H plus ion concentration is 0.020 molar. So that should lead us to the pH quickly. 0.020 molar H plus, might as well label it, takes very little time to do so. And in this case, 2 times 10 to the minus 2 is the molarity in scientific notation. The pH of this, 1.7. You'll notice, if you're thoughtful, that this is the same pH that we had earlier when we looked at the strong acid in 1D. And this illustrates a common misconception students have. They'll say, oh, pH 1.7, that means it's a strong acid. No, it doesn't. A strong acid is a molecule. It's not a solution. In this case, the reason the pH values are the same is because here we have a very dilute strong acid, 0.02 molar HCl, has the same pH as this 0.34 molar solution of lactic acid.